Hello students, in this lecture we're going to talk about a new topic, the carbohydrates, and I'm sure this will be a series, and so this will be carbohydrates part 1. So here we're going to talk about the carbohydrates. Now carbohydrates have the basic formula for carbohydrates would be CH2O. You can have any number of those, but a better way to write this would be this: carbon, and then water, and then you can have as many of these units as you wish. And so you see that a carbohydrate is just the hydration of carbons, and so hydrated carbon. And so a carbohydrate is just hydrated carbon. And as you can see here we have our carbon and our water is our hydration. And so that's a carbohydrate. Let's draw ourselves a very simple carbohydrate first. Simple carbohydrate would be something like this. Let's see what side I'll put this on. This is the one we've done already. OH, H, and CH2OH. Here we have a very simple carbohydrate, and this carbohydrate is glyceraldehyde. And the stereoisomer that we've drawn here using our Fisher projection is going to be L-glyceraldehyde. Now, if you can remember from our study of the amino acids and the proteins, the amino acids, the common amino acids found in living organisms, are going to be L amino acids, and they're based on L-glyceraldehyde. However, our carbohydrates are different. For the carbohydrates, you wouldn't use L-glyceraldehyde. So this is not the one you would use for our carbohydrates. For the carbohydrates, you're going to use D-glyceraldehyde. So let's get rid of that there. Didn't take too long to redraw that. And so here we have L-glyceraldehyde. However, that's not the one. L-glyceraldehyde is this is the compound that our L amino acids are based on. However, compound that our carbohydrates are based on will be its mirror image. And this is D-glyceraldehyde. And so D-glyceraldehyde is going to be the carbohydrate we'll be using. So if we look at D-glyceraldehyde here, you can see that here, this is our chiral carbon. And this carbon is going to be going this way. It's going to be R. So this carbon is going to have the R configuration, and this one will have the S configuration. So in all of the carbohydrates that are found in living organisms, well, most of them, nearly, I'm sure there's an exception somewhere, all the ones that we're concerned with, that highest chiral carbon, the highest number of chiral carbon, is going to have the R configuration, or it's going to have the R configuration, and that will be the D isomer, or the D stereoisomer. And so this compound is D-glyceraldehyde. Let us, I don't know, let's give you one more example. So let's to give one more example, and then we're going to get some more basic information. Let's go. Let's make a 4-carbon. A 4-carbon carbohydrate. Here we're going to have aldehyde functional group. It doesn't have to be an aldehyde there. You can actually have a ketone here, but we're going to keep it as an aldehyde. Actually, it would make more sense. Well, no, let me show you something. So here we're going to have, let's put this over here. So there's a chiral center here, and the second one is going to be a chiral center. Let's just put it on the same side. And if we put it over here, yes, let's put it over here. And we're only going to have 4 carbons. We number these carbons 1, 2, 3, 4. There are 2 chiral centers. Carbon 2 has a chiral center, and carbon 3 is a chiral center. So highest number is 3. Since that has an R configuration, this compound is D something. It's D something. And so since that second carbon is also has an R configuration, we call this compound erythrose. But the main thing to remember, the highest number chirality, this highest number here, is going to always have the R configuration, and those will all be the D isomers, always the D isomer. Let me show you one more example here. One more thing I want to show you here. The carbohydrate does not have to be an aldehyde. It can be a ketone. So here we can have CH2OH here. And now we can put our ketone group here. And then we can have let's do 4. And CH2OH. Now this compound here, because it's a ketone, it only has 1 chiral center. And this compound, 4-carbon, this compound is going to be called erythrulose. Erythrulose. And of course it's D, because this highest chiral center, the highest number chiral center, has the R configuration. So this is going to be D-erythrulose. So all of our compounds, everything that we find in the living organisms, all the ones that we'll discuss in a biochemistry class, are going to have the D configuration, like D-glyceraldehyde. Is there anything else I want to talk about here? That's it. And on the next slide, on the next clip, we'll explore some deeper background information about carbohydrates. So this is where we're going. The carbohydrates. We're going to go from 3 carbons all the way up to 7 carbons. We're going to try to figure out what are these things, what are their names. Let's give a little more background information for these carbohydrates. Carbohydrates can be found in a variety of forms. The most common carbohydrate is going to be a 6-membered ring. So the most common carbohydrate is going to it's going to look like this. It's going to be a 6-membered ring. And if you just have one carbohydrate, we call this a monosaccharide. So if it's just one sugar, we just call it a sugar, or a simple sugar. So this is a monosaccharide. S-A-C-C-H-A-R-I-D-E. It's a monosaccharide. A monosaccharide is also known as a simple sugar. And you think, well, the most common carbohydrate is going to be glyceraldehyde, because that's what we've been talking about forever. But it's really not. The most common one is going to be glucose. Glucose is going to be our most common carbohydrate. And so we can also write this as just put a G there for glucose. Now, if you just have one simple sugar, we call that a monosaccharide. So there would be a variety of forms. We could also have, we could also put two simple sugars together. If we put two simple sugars together, we no longer call this a monosaccharide. We call it one of the oligosaccharides. And so this specific oligosaccharide is called a disaccharide, because there are two sugars. And as you can surmise, saccharide means sugar. So we have a disaccharide here. And I hope I'm spelling saccharide correctly. Okay, this is a disaccharide. Now, if you have anywhere between 2 sugars and 10 sugars, so you can have 10 sugars. Let's see how we can do this. A sugar here. A sugar here. And then this is going to be tough. Okay, we have another sugar. And here, what we can do here, it doesn't want to work. I'll just use a different color. That may make it more visible. I'm doing something wrong here. Not sure what it is. Okay, here we are. I don't know why that won't stay on the pen. There we are. And so N equals, N can be anywhere from, so we're going to have, we already have 2, so this can go from, I'm having an issue here and I don't know what it is. It keeps changing. It doesn't want to work. So N can be, let's just say N is 8. And so anywhere from 2 sugars to 10 sugars, we call those oligosaccharides, because the Greek word oligo means many, or few, means few. And so this is an oligosaccharide. So a disaccharide is an oligosaccharide. So if you have 2, well, let's just make ourselves a chart. Let's go to a new slide here. Let's make ourselves a chart. Here we can have the number of sugars, and then we can have the prefix. I think that's all we need, but we'll see. And so, if we have 2 sugars, the prefix is di. And so that's a disaccharide. If we have 3 sugars, the prefix is going to be tri. And so we would have a trisaccharide. And so a disaccharide and a trisaccharide, both of those are types of oligosaccharides. If we have 4 sugars, I think it's going to be a tetrasaccharide. monosaccharide. And then if we have 5 sugars, we're going to have a pentasaccharide. Okay. But we don't really once we get beyond 3, we just call them an oligosaccharide. But you can keep going, 6, 7, 8, 9, and then 10 would be a decasaccharide, I guess. A decasaccharide. But these here, when you get from 4 to 10, you don't really name those specifically. You don't name those empirically. You just call them oligosaccharides. So if you have 2 sugars, you have a disaccharide. If you have 3 sugars, you have a trisaccharide. And anything beyond 3 is an oligosaccharide, even though 2 is still an oligosaccharide. Okay, let us move on to the next one. What if we had a sugar that had even more? For example, here we have a sugar. I'm just going to draw it like this for now. Okay, and this is a sugar, sugar, sugar. But here we can have it, let's say we have as many of n is greater than 8. N is greater than 8. So 11 and beyond. 11 to infinity and beyond. So if we have a polymer of sugars where there are more than 10 sugars, it ceases to be an oligosaccharide. At that point, we call it and again, this is semantic, because if you only have 11, somebody's going to say, well, that's still an oligosaccharide. But you have to draw the line somewhere. So conventionally, 11 and beyond is going to be a polysaccharide. Polysaccharide, because poly means many. So we have a polysaccharide. And polysaccharide include things like starch that's found in plants, and glycogen that's found in animals. These are our polysaccharides. And so that's a little background information on our polymers, our simple sugars, the oligosaccharides, and the polymers, or the polysaccharides. And we'll stop there on this clip. On this clip, we're going to look at the classification of our monosaccharides. We can classify monosaccharides based on 2 criteria: the number of carbons and the functional group, or the aldehyde or ketone functional group. Okay, let's draw first our simplest aldehyde, which is going to be, our smallest is going to be a 3 carbon. This is going to be glyceraldehyde. Again, we're going to make sure we put the OH to the right. And so that's going to make this is going to be D-glyceraldehyde. D-glyceraldehyde. Now, D-glyceraldehyde, because it has an aldehyde functional group, we call this an aldose. So D-glyceraldehyde is an aldose. And because it has 3 carbons, it's a triose. So D-glyceraldehyde is an aldose, and it is a triose. And so we can call D-glyceraldehyde an aldotriose. Okay. let's look at another compound, another sugar, where the carbonyl is not on the one carbon, but it's on the two carbon. And so we would have something that looks like this, CH2OH. So now here we have a carbon with a chiral center. And so this is our chiral center. But if we put our carbonyl, if we make our number 2 carbon carbonyl carbon, now we have no chirality here. And this compound is just dihydroxyacetone. Dihydroxyacetone. And dihydroxyacetone, it is a carbohydrate, but there are no stereoisomers here. There's no D or L form. Because it has a ketone functional group here, we call this a ketose. And because there are 3 carbons, it's still a triose. And so we can call dihydroxyacetone a ketotriose. So dihydroxyacetone is a ketotriose. Okay. Very good. Excellent, excellent. Now, for our aldotriose, if we go back to our aldotriose, this carbon 2, this is a chiral center, and so we can have there are 2 aldotrioses, because that can be either here, this can be either D or L, or RS would be better here. And for our ketotriose, there is no chiral center, and so there's only one ketotriose. Let's do another one. Let's go to 4 carbons. Let's go to 4 carbons, and we're only going to stay within the D family, but you have to remember there are L's. And so for D-glyceraldehyde, the mirror image is L-glyceraldehyde. Let me draw that, just so you'll know how things work. So I'm going to draw C. Well, that'll be an H. C-OH. This is the mirror image, H. CH2OH. And this is going to be, I'm just going to put L here, L-glyceraldehyde. It's the mirror image. But we aren't going to be talking about these, so that's L-glyceraldehyde there. Let's go to 4 carbons. Okay. First, let's do our aldose. So here we're going to have COH, H. There's a chiral center, COH. And since we're talking about just D's, that one has to be to the right, and CH2OH. Now this compound here, of course, it is an aldose. This makes it an aldose, and it has 4 carbons, so this monosaccharide is a tetrose. So we can call this an aldotetrose. Since there are 2 chiral centers here for your aldotet, so you can have, since there are 2 chiral centers, that's 2 squared, you can have 4 aldotetroses. But again, we aren't going to change this one. We're going to keep this one in the R configuration. So we're going to always keep D. Let's change this one. So we can have here C double bond H. There's our aldehyde. And we're going to change this here. We're going to give this one, this one is going to have the S configuration. And we're going to keep the R configuration here. And CH2OH. And so here, this is another aldo tetrose, a D-aldo tetrose, because we're going to keep that D configuration. We're keeping D there, keeping that to the right to make it D. So this has an R configuration here. Let me ask you this. Dr. Merida. Okay, and so here we have an aldo tetrose, where the number 2 carbon has here the S configuration. So this is the S configuration. And so let us name these 2 aldo tetroses. Now the first one here, the first aldo tetrose, is going to be called erythrose. And we've already seen this one. I'm going to put here, this is erythrose. This is going to be erythrose, and again it's D, because we're keeping the D configuration. And then this D monosaccharide, or this D aldotetrose, is going to be called D-threose. D-threose. And again, we have a mirror image of both of these. The mirror image of both of these where everything flips. Those are going to be our L isomers, but we don't see L isomers, so we aren't going to talk about those. Okay? And we can continue this, but we're not going to continue it on this slide. So here we have D-erythrose and D-threose, two of our 4 D-aldo tetroses.